Today I start one important topics related to LP space. Okay, that means in measure theory these topics are discussed. We also in previous class discussed some positive variation, some negative variation for some measure and positive variation for some measure and total variation for some measure and mutually singular measure and mutually singular sign measure. Okay, we also discuss in previous class. Today I talk about one important theorem related to measure theory. This one is Jordan decomposition theorem. Okay, we also start this theorem. We write this statement first. Okay, we just write the that means theorem name, Jordan decomposition theorem. Okay, now we're going to the statement of this theorem. Okay, statement of this theorem. Let X, this algebra mu, be a sign measure space, be a sign measure space. Okay, then then there exist two mutually singular measure mu plus mu minus on X this algebra. Okay, such that mu equal to mu plus difference mu minus. Okay, this representation is unique. This representation be unique. Okay, so we're going to prove of that. So what we write here, just sign measure space. Sign measure means we know about that the range of mu if any set belongs to minus infinity to plus infinity. Okay, where A belongs to this algebra. And what we mean about that, two mutually singular measure. Mutually singular measure mu plus and mu minus. We know about that mu plus equal to what? Mu plus some E equal to mu of P intersection E. Okay, obviously greater than equal to 0, and mu minus of E equal to minus mu of N intersection E, obviously greater than equal to 0 because N negative set and P positive set. Okay, then obviously this mu plus and mu minus are belongs to 0 plus infinity. Okay, and then what happened, we also shows about that there exists two mutually singular measure. Okay, that means these measures are mutually singular. That means mu plus and mu minus obviously mutually singular because we know about that some Pn, here we write n and here write p, then obviously this one are singular measure. Okay, that means measure are 0. And then what happened, then we also talk about that this representation be unique. Okay, that means in Hahn decomposition theorem we also show about that set decompose into some disjoint sets. Okay, positive set and negative set. But here we also in Jordan decomposition theorem this measure is decomposed by two, that means variation. Okay, two positive variation or positive variation and negative variation for a measure. Okay, this that means these two variations are decomposed one measure. Okay, and obviously this representation be unique. So we also going to prove of that important theorem, Jordan decomposition theorem. We're going to prove of that. Okay, so we erase that portion and going to prove of that. We write here proof. What happens? Let Pn be a Hahn decomposition for Hahn decomposition of X. Okay, we know about that P be positive set and N be negative set, and we also discussed in earlier or previous classes. Okay, so now we define mu plus and mu minus this algebra to 0 plus infinity by mu plus of E equal to what? Here we write mu of P intersection E. Okay, and mu minus of E equal to what? Minus of mu N intersection E. Okay, for all E belongs to this algebra. Okay, then what happened? Then mu plus and mu minus are measured on X descript A. Okay, now note that here mu plus n equal to, or known about that mu of P intersection n equal to mu of phi, and we known about that mu of phi equal to 0. Okay, then what happened? Then mu of minus P equal to what? Mu of n intersection P equal to mu of phi equal to 0. Okay, sorry, here minus. Okay, I write wrong, some wrong. Okay, then what happened here? Hence we know about that mu plus and mu minus are mutually singular. Okay, mutually singular measure. Okay, because all are belong greater than equal to 0, so measure. Okay, then what happened? Then we erase that portion. Okay, all are known. Mu plus we know about that, mu minus we know about that, and obviously this one are mutually singular, we also known in previous. Okay, but we write it here. Now we're going to forward. We'll erase that portion and going to further discussion of another portion. Okay, so what portion we discuss here? We write it now. For E belongs to this script A or algebra, we have what we have. We write it now. Mu of E equal to what? Mu of E intersection X. Mu of E intersection X equal to what? Mu of E intersection P union N. We X equal to P union N. We get from here. We get from one important theorem. This one is Hahn decomposition theorem. Okay, so we're going to forward. Okay, what? Mu of E intersection P union E intersection N. Okay, then what happened? We write it now. Sorry, not here. This one just intersection rule. Intersection and unions are commute. Okay, not commute, this one are, that means distributed. Okay, intersection distributed with unions. So here we write it now, intersection P plus mu of E intersection N. Why? Mu is finitely additive. Okay, finitely additive. Mu is finitely additive. Okay, now we're going to forward discussion of that. This one is mu plus E and this one is minus mu minus E. Okay, then what happened? This one equal to mu plus difference mu minus of E. Okay, so we are going to this one where mu equal to mu plus difference mu minus. Okay, now we're done just uniqueness part, but we also going to this discussion of that mu equal to positive variation, difference, negative variation for mu. Okay, so we're now going to uniqueness of representation. We erase that portion and going to uniqueness of representation. Okay, now we write it here, uniqueness of representation. Let P1 N1 be another Hahn decomposition, be another Hahn decomposition of X. Okay, let E belongs to the script A. Then what happened? Then E intersection P difference P1 subset of P. Okay, this implies that mu of E intersection P difference P1 greater than equal to 0. Okay, not a problem at all. P1 and N1 another Hahn decomposition for X. So E intersection P difference P1 subset of P. Okay, now obviously mu of E intersection subset of P means greater than equal to 0, this measure, and again we write it now, and E intersection P difference P1 equal to what? Equal to E intersection P intersection P1 complement. Okay, then what happened? Then E intersection here P intersection P1 in complement equal to what? N1. We write it now, P1 complement equal to N1. Okay, because P1 union N1 equal to X, P1 union N1 equal to X, so P1 complement equal to N1. So what happened here? We write it now, subset of N1. Okay, E intersection P intersection N1, that means obviously subset of N1. Then we write it in this way, mu of E intersection P difference P1, okay, less than equal to 0, because mu N1, okay, mu N1 what? Less than equal to 0. So we get from this part star and this part double star. Okay, what we get? We get mu of E intersection P difference P1 equal to 0. Okay, now what we do? We erase that portion and going to further discussion of that. Okay, so too easily we discuss this step. Okay, now we're going to forward step. Forward step, we write it now. Now mu of, okay, mu of E intersection P union P1 equal to what? Equal to, we write it mu of E intersection P union p1 difference p. Okay, not a problem at all. So this one equal to mu e intersection p. Okay, mu intersection p union of e intersection p1 difference p. Okay, then what happened? Then we write it now, mu of e intersection p plus mu of e intersection p1 difference p. Okay, because e intersection p and this one intersection e intersection p1 difference p, okay, are mutually disjoint. Okay, so not a problem at all, this one. Okay, mu intersection p and mu intersection p difference p1 obviously mutually disjoint, so we write it, this one is, and mu is finitely additive, so we write this one. Then what happened? This one is equal to 0, we prove it, so this one equal to mu of e intersection p. So what we see about that, this one equal to mu of e intersection p, sorry, mu of e intersection p union p1 equal to mu of e intersection p. So we write it similarly. We're doing this procedure. We write p difference p1. Then what happened? We also get this one, mu of e intersection p equal to, okay, sorry, here p1 equal to mu of e intersection p1 union p. Okay, here what we get, this one equal to this one e intersection p, and if similarly we do it, then what happens? Mu of e intersection p1 equal to mu of e intersection p1 union p. That means this one are same, we just interchange p and p1, then this one happen. Okay, I understand, not a problem at all, I think. Then what happened? Then we erase that portion and we arrive this needed uniqueness condition. Okay, so what happened? We write it now, mu of e intersection p equal to mu of e intersection p1 equal to mu of e intersection p union p1. Okay, not a problem at all. So this one equal to what? Mu plus e. Okay, then what happened? We write it now, thus mu plus is independent from Hahn decomposition. Okay, then similarly what happened? Similarly we do it, then we also going to further discussion of that, mu minus is independent. Okay, from Hahn decomposition. Okay, so the representation mu equal to mu plus difference mu minus, this one is unique. Okay, not a problem at all. Any problem here? I think not a problem. Okay, so what we see any measure, obviously that means sum expressed by positive variation and negative variation. Okay, that means any measure, obviously difference of positive variation and negative variation, any measure equal to for difference of positive variation and negative variation, and obviously, and this representation is unique, so we do it easily. Okay, all are seen about it. I think this one is too easy. All are done this theorem. Okay, any problem is here? I think not a problem. So today I discuss one important theorem, Jordan decomposition theorem. If you get this type of video, please subscribe my channel, and if you want to get this video, and obviously if you prefer this video, then give like, and if you have any comment, question, suggestion, please write it in comment box. So today I stop here. Okay,